Hi, so I'm getting ready to have a look at this 70cm transverter I designed, and I thought before we did it'd be a good idea to actually walk through some of the more complicated RF measurements we're going to do on it, how we make them, why we care, and how they affect the performance of our circuit. And I thought an excellent place to start with that would be having a look at noise and noise figure, because this is going to be one of the key parameters of the first block we're going to analyse. Now I'm going to do this in two parts. The first part will be purely theory, and then in the second video we'll have a look at how we measure it using the Y factor and what bits of lab equipment we need to do this, and see if we can improve the performance of our circuit. So before we get going on this, what do we mean by when we talk about noise in the context of electronics? We define noise as the unwanted disturbance of an electronic signal. So if I have an input signal to my circuit that is a relatively clean sine wave, and it comes out looking all jagged and horrible, well, these perturbations are what we call noise. Now, noise can come from many sources, but the one we're going to look at today is called thermal noise, or also known as Johnson noise. This is caused because the electrons in our conductors, so that's our coax and our PCB traces, will vibrate at any temperature above absolute zero, which is minus 273 degrees Celsius. The higher the temperature, the larger these vibrations are, which is why some of the most sophisticated sensors used for lab equipment and particle detection are cooled with liquid nitrogen or helium to try and minimize this thermal noise. We say that thermal noise is spectrally flat, or sometimes called white noise. And what we mean by this is that if we sort of plotted the noise against frequency, we would see that it is constant. So the noise power in any given bandwidth doesn't depend on what frequency we're measuring it at. The thermal noise power in a 1 Hz bandwidth at 1 MHz is the same as the thermal noise in that same bandwidth at 1 GHz. And because it's constant with frequency, the noise power in a 2 Hz bandwidth will be twice that compared to that in a 1 Hz bandwidth. 10 Hz bandwidth will be 10 times that, and so on. So, the expression for thermal noise is as follows. It's not especially complicated. We've already established that it's proportional to bandwidth, which is this capital B term. T is temperature in Kelvin. So a change of 1 Kelvin is the same as a change of 1 Celsius, but the 0 point, so 0 Kelvin is defined at absolute zero rather than at 0 degrees Celsius, which is the freezing point of water. And you can convert from Celsius to Kelvin by adding roughly 273. So we've got this thermal power that is generated purely from the fact that we have our circuit is at temperatures above absolute zero, but the amount of power generated is absolutely tiny. At 290 Kelvin, which is equivalent to roughly 17 Celsius, the thermal noise is minus 174 dBm per Hertz, or 4,000ths of a billionth of a watt. So incredibly small indeed. So we've established that the noise at room temperature should be about minus 174 dBm per Hertz. So let's have a look at my spectrum analyzer. Here we go. So what we're doing is we're looking at 10 GHz and we're seeing what power we're getting in a 1 Hz bandwidth. And you can see that this is giving a reading of roughly minus 148 dBm per Hertz, which is much higher. So what's going on here? So let's do an example. Let's say this is what is coming out of our receive antenna. There's no signals present and we have no sources of interference. So in a perfect world where we have 17 degrees C ambient temperature, this level will be at minus 174 dBm per Hertz, like we've discussed earlier. Now we start receiving something, so our signal appears on top of this. And the amount of signal power we get relative to the amount of noise power will determine how clear our signal is, or if it was a digital signal, will be linked towards the error rate we get. We call this signal to noise ratio, or SNR, and we define it as the power of the signal divided by the power of the noise. It's important to mention that SNR requires that the signal and the noise are defined in some bandwidth. If we take this waveform we have here, well, we'll say our signal is between here and here, which means our signal power will be the area in here, and our noise power will be the area in these bits here, and that will give us some number. But if we went and applied a filter to this, so we filtered our signal such that we were only considering things within a bandwidth like this, well then our signal power is still the same because the area here is still the same, but our noise power has just got a lot smaller because it's now only these two sections rather than the whole width. I mentioned this as a lot of the amateur digital modes by K1JT, such as Whisper and FT8, define SNR for a 2.5 kHz noise bandwidth, but then have a signal that is either tens of hertz or like single digits hertz wide, which sounds remarkably impressive reporting decodes at sort of -25, -29 dB, so a signal that is roughly 200 times smaller than the noise. However, the first thing it does in decoding it is apply a very sharp filter, so the SNR is not quite as impressive as it originally sounds. Anyway, rant over. So here we have our signal. So we have our signal here and our noise. So what we have is we have our signal and our noise. These are both time varying, but for the sake of brevity I'm not going to write that down. And we put them into some amplifier we have, and what we'd expect to get out. So this green one is our original signal, and we'd have expected the amplitude of everything to have got bigger. So let's say this amplifier has a gain of G. What we'd expect to get out is the gain times what we put in. So G times S plus N, or alternatively GS plus GN. And if we consider the signal to noise ratio at the input, well, this is S over N. And if we consider the signal to noise on the output, it would be GS over GN, which is the same thing. However, what we'll actually see is it won't be this nice, unfortunately, and the output will look more something like this. So you can see that we have the same signal power, but our noise floor relative to our signal has increased. So our SNR has gone down effectively, because on the top we have GS, and on the bottom we have GN plus some additional noise, so plus extra. So our SNR has gone down as a result of going through this amplifier, and that is what I'd like to have a look at now, and where noise figure comes in. So here we have 3 stages of amplification, and throughout this I'm going to assume that we generally want positive gain, i.e. our signal is getting larger as it goes through our receive chain. So we have our input, which has some signal plus our thermal noise, and we have some output. And in this scenario, we'd expect the output to be G1 times G2 times G3 of S plus N. And for the same argument we made earlier, the SNR of this is G1, G2, G3 of S over G1, G2, G3, N, which is, those cancel out and give us our initial SNR of S over N. However, it doesn't work like this, because what we have is any active component can be modelled as having a noise source at the input. Now, these noises are white noise sources, they are spectrally flat, but they contribute towards the noise at the output. So we define this noise source as being as the input of the device. So this N1 comes from G1, so we're modelling some amplifier as a noise source at the input to a perfect noiseless amplifier with a gain of G1. So let's work through what we get at the output. Well, S plus N is going through the first amplifier and the second and the third. So at our output we're going to have G1, G2, G3, S plus G1, G2, G3, N, exactly as before. However, we're going to have some additional terms. So this N1, this noise source at the input of amplifier 1, this is also going to go up here and through all 3 amplifiers, which means it is going to be subjected to the same gain. So there's going to be G1, G2, G3 times N1. This noise source here, N2, well, this is only going to go through these 2 amplifiers. So that is going to be plus G2, G3 times the noise source at the input of device 2. And N3 is only going through the third amplifier. So that will be plus G3, N3. So our signal is still only this term here, but our noise is now made up of a much more complicated expression of all of this lot. So that means our SNR is going to have gone down. And what's important to note here is that, again, assuming that we generally have positive gain through our circuit, is that N1 is the most important contributor, because N1 is going to go through all these three stages of amplification, whereas N2 is only going to go through these two, and N3 is only going to go through this last one to get it to the output. So it's important that we prioritise noise as early on in the circuit as possible, because once we've got noise into our signal, we can't remove it whilst keeping the bandwidth the same. There are clever digital signal processing techniques you can do based on knowledge of the signal, but from an analog perspective, once we've degraded that SNR, we can't do anything about it. So now we know that all the components in our system will degrade SNR, we really need a way to quantify how much that degradation is. And there are generally three ways of doing this, which are useful in different scenarios. So the first one is noise factor. So that is the straightforward ratio of the SNR at the input to the SNR at the output. Now we know the SNR is going to have got worse at the output, so this will always be a term bigger than 1. Other way to do it is noise figure, which is just noise factor expressed in dB. RF engineers tend to like everything in dB. Though in terms of actual quantifiable things, this is only really useful as the noise figure represents how much worse your SNR has got in dB. So if you have a signal with 6 dB SNR and shove it through something with 3 dB of noise figure, you're going to have 6 minus 3 dB SNR roughly at the output. And the way that I tend to prefer it, particularly when chaining multiple devices together, is to think about it as noise temperature. Now we said earlier that noise power was equal to K times T times B. Well, K is a constant, B is our signal bandwidth, which is likely to be a constant throughout our system, so this means we can use, in the context of noise, we can use temperature and power interchangeably, because the two are directly related to each other, just multiplied by some constant. So what I have here is I've got our circuit from before, and I've just replaced our various sort of noise power sources with temperature sources. And again, the excess noise at the output will be this expression from before. And what we'd ideally like to do is to merge all this circuit together into one thing with some effective gain and a single value for what this noise temperature is going to be at the input. Well, the effective gain of the whole thing is going to just be the gain through the whole system, so that's just going to be G1, G2, G3. And our equivalent temperature, well, this temperature is at the input, and this temperature at the input would give a noise component at the output of G1, G2, G3 times TE. So if we take our noise component at the output, which we said is this expression, and then divide it all by G1, G2, G3, that will give us our effective noise temperature. So what we'll get there is T1 plus T2 over G1 plus T3 over G1, G2. The general term is it will be divided by the gain of all the stages in front of it. And this again agrees that the first stages have the most important contribution to noise temperature, because again, assuming gain is positive and going up, well, these terms at the bottom should be getting larger and larger and larger, so the contribution to this entire sum will be getting smaller and smaller and smaller. I will stress that there are formulas for directly working in terms of noise figure or noise factor and cascading them between multiple devices, but you end up with a lot of minus ones in the formula that are easy to get in the wrong place or forget, so I tend to work into temperature as I find this expression much more straightforward. Right, that's quite a lot of theory for one day, so I'll just summarise and then we'll move on to practical stuff next time. So in summary, thermal noise is present in all systems and it's caused by the electrons vibrating. This noise power is proportional to the temperature at which our devices are at. However, generally, especially in an amateur scenario, we can't do much about this. All active devices add noise. At best you can do is you can not degrade SNR, and everything in reality will degrade it a little bit. One handy rule of thumb is in purely passive devices, the noise figure is equal to their loss. So our input and our output are at the same temperature, so our noise power is going to be the same. Whereas if we have, 3 dB of loss, so we lose half our power going through the device, well, our signal's got 3 dB smaller, and our Noise has remained constant, it's at the same temperature, so our SNR has just got 3 dB worse. Devices at the start of the chain matter most. This is because everything is divided by the gain of the stages in front of it. So if we have an amplifier right up next to the antenna, so a masthead preamp, well, any subsequent noise figure, including that of the cable back to the shack, will then be divided by the gain of that amplifier, which will help to minimize our noise figure as much as possible. And under most conditions, noise figure in dB is roughly how much your SNR will degrade as it goes through that device. So, I'll call it quits there. If you have any comments or feedback, I'm on Twitter at M0WUT, or comments down in the description. So thank you very much, and I hope you'll join me next time when we go and measure the noise figure of a 70 SEMS LNA.